Our next speaker is Emanuele Panella. He'll tell us about charged black holes in ESP.
Okay. Can you hear me? Does it work? Yeah? Good. Okay. Hello. First, let me thank the organizers for giving me the opportunity to speak. For those of you who are expecting a cosmology talk, you're out of luck. The best I can give you is the sitter. But I'll be talking about maybe something interesting anyways. So this is work in collaboration with Anna Clemente and Robbie Henninger at the University of Barcelona and Andrew Vesco at King's College London. It will probably appear very soon on the archive, but there is a bunch of other work that kind of leaked into this presentation anyway, so I've put them all up. This is the outline of the talk. I'll first say a couple of words about GR in 2 + 1 dimension, then give some way to construct these quantum-corrected black holes, and then maybe we can play about with them in the thermodynamic a little bit. So as physicists, we often like, as Victor was saying before, to go down in dimensions to kind of simplify calculation, learn things that we can then uplift in 4 dimensions. But if you are a black hole physicist, then maybe you are out of luck because GR in 2 + 1 dimension is boring. So either you get away from pure Einstein's gravity, or yeah, you're actually out of luck. There is no propagating graviton mode, and so if you want a vacuum solution that has, you know, a horizon and black holes and stuff, you can only go to negative cosmological constant and ADS. But if you're interested in, you know, cosmological spacetimes like de Sitter, you can get that. And the reason is that G3M here, that usually gives you a length scale for a black hole horizon, actually in 3 dimensions gives you just a dimensionless number, and what that represents is our angular deficit. So point masses in 2 + 1 dimensions actually correspond to conical singularities. But you can try and do something else. Maybe you can try and back react some quantum field on the geometry and hope that that actually hides your conical singularity in some black hole horizon. And doing the back reaction problem involves solving the semi-Larsen equation. That's very hard in general, so you cannot do it exactly. But linear calculations actually suggest that indeed it seems like you can dress the singularity with a Planckian-sized horizon. But can we do better? And yes, we can. We can use the SCFT correspondence that turns out to be a very powerful tool to solve the semi-classical Einstein equation exactly, with some caveats. So what are we going to do? Well, these are the usual ingredients in the SCFT. We're going to work in the large n limits such that the dual gravitational theory classicalizes to something like just classical Einstein's gravity. And then, as a reminder, but I don't think it has to be reminded, the IR divergences in the bulk correspond in a dual field theory to UV divergences. And usually you take care of this by introducing a cutoff surface some distance little l away from the conformal boundary. You calculate the local counter terms in a minimal subtraction scheme, and then you send the cutoff surface back to the conformal boundary, the renormalized theory. But what if you don't do that? What if you don't send the cutoff surface back to the boundary and you actually make it dynamical? You give it an action, it becomes a brane with some tension. What is the theory that's induced on the brane, like an observer sitting on a brane would perceive? And effectively, it just becomes the theory that you had before, your old CFT, but it starts coupling to the metric induced on the brane. And I mean, the idea here is that as you're dragging the conformal boundary into the bulk, the CFT starts coupling to the brane, and so it back reacts on it. And that led in 2002 to a conjecture by Empran, Caloper, and Fabry that if you find in the bulk an ADS d + 1 dimensional black hole that localizes on such a brane, then the induced metric on the brane solves exactly the back reaction problem in the semi-classical Einstein's equation for the d-dimensional theory. So that's our line to kind of try and solve the back reaction problem exactly. We need to find such a solution. And such a solution, if you're interested in 2 + 1 dimensional gravity on the brane, is the ADS4C metric. For those that are not familiar, this is just a metric that describes a pair of accelerating black holes in ADS space, where the acceleration is given by 1 over little l, and this little l is the same as the one I was mentioning before, in the sense that as I want a black hole that is closer and closer to the boundary, I basically get a larger and larger acceleration, so indeed the two will match in the holographic construction. And maybe a key property here to mention is that x equals 0 is a so-called umbilic surface, and that will help us a lot in the holographic construction. An umbilic surface is just a surface where the extrinsic curvature is proportional to the induced metric on the surface. That will actually simplify a lot calculations. And maybe another point is that when you're working with ADS-C metrics, you need to be careful about conical singularities, which correspond to zeros of this g of x function. Two of them are physical, and they correspond to conical singularities here, where the acceleration of these black holes in ADS, you can picture it as given by some cosmic string that hangs from the horizon and is pulling your black hole. Where the black hole is being pulled, you get a conical singularities, but there is also some singularities that you can just remove by an appropriate identification of the angular coordinate, and those are not physical, so you need to be careful with that. But once you know that, you can take your both spacetime and start doing some spacetime surgery to end up with something that then gives you a black hole localized on the brane. So you introduce that brane at x equals 0, you delete all this part of the spacetime, you also delete everything that's bigger than this x1, which is basically the location of the conical singularity, which you can remove with the coordinate identification. And removing everything bigger than x1 basically means you're removing the cosmic string that's pulling your black hole. Then you take your ADS space, you copy it, and then you glue it together across the brane. And when you do that, here the umbilic property of the x equals 0 surface really helps you a lot, because when you're gluing two spacetimes together, you need to make sure that you're satisfying something called the Israelite junction conditions, and they basically reduce, because of these umbilic properties, to just having the tension of the brane being the thing that gives you the acceleration to the black hole. And that makes sense physically, because we have removed the cosmic string, so something needs to accelerate the black hole, and that something is indeed the brane that we're going to do holography with, fundamentally. Good, so now we have kind of described what the construction is from the point of view of the bulk. Let's see what we get on the brane. You can go through and derive the equation of motion for the theory induced on the brane by basically integrating out the UV degrees of freedom in the CFT that you have removed by introducing the cutoff, and you get something like this. So this first part is the semi-classical Einstein's equation. We'll be looking at charges, a charge solution, and so we just introduce a charge in the bulk theory. So in the bulk we have Einstein-Maxwell actually, and this is why we also get some type of Einstein-Maxwell on the brane. But then we also get higher order, actually an infinite tower of higher curvature corrections, which are controlled by these little L squared parameters, and actually you're going to have L4 and so on. So as we take little l close to 0, then to good approximation we are in just Einstein's gravity, but actually we do have an infinite tower of terms. And then we also have Maxwell's equation on the brane. Now an important point is that actually the electromagnetic theory does not properly localize on branes, and this has been studied back in the days when people were actually studying brane works for maybe phenomenological reason. You cannot basically localize spin 1 fields on the brane as you do with gravitative modes. And that basically means that in the blackening factor of the backreacted geometry, which we can just read off from the metric induced on the brane by this holographic construction, the charged part doesn't go as the logarithm of the radius as you would expect in 2+1 dimension. It actually goes as 1 over r squared, which is what you have in 4 dimensions. So there's this caveat here. But fundamentally what you get is this bit here is just the conical defect in the S3, so it's the thing you usually have. And everything that has power of L is the produce of the back reaction fundamentally. So you get these 2 times here. The blackening factor, for those that are familiar with de Sitter physics, is exactly the blackening factor of the higher dimensional Reisner-Nordstrom de Sitter black hole. And so with it, it shares the the horizon structure. It has an internal, an outer, and a cosmological horizon, and you have all your limits. Maybe of interest is the Nariai limit, which is the biggest black hole that you can fit in the Sitter space without having a naked singularity. If you take all of these 2 limits together, you get the ultra-cold limit. Now, we have a solution to the semi-classical Einstein's equation, but we actually don't know what source the semi-classical Einstein's equation, because we have just read the solution. But we can fix that by just plugging in the solution in the equation of motion and expanding the sources in power of L squared and doing a matching. And this is what you get. And for the stress tensor, you can actually do the semi-classical perturbation calculation in just Einstein's theory with maybe a conformally coupled scalar, and you would see that what you get is exactly this structure for the stress tensor, and you can also match the higher order and so on. And so that really is a very good sanity check that we are doing what we claim we are doing. We are solving the semi-classical Einstein's equation, albeit in a higher curvature theory of gravity. Now this is the phase space of the black hole we are looking at. It's exactly the same as the Reisner and Nordstrom, at least qualitatively, where everything in the white region is a bona fide black hole, everything in the gray region is actually a naked singularity, so you really want to be in this region. And interestingly, as you tune the back reaction parameter, when this nu is literally little l, it's just a normalized version between 0 and 1, you approach this red contour, which is the actual four-dimensional Reisner-Nordstrom black hole. So as you increase the back reaction, the black hole looks more and more four-dimensional. But you actually can deform these profiles. So things that are technically not allowed in the four-dimensional theory get allowed, black holes get allowed in the lower one, depending on the value of the back reaction. Now, regarding thermodynamics, the story is pretty much the same. There is a first law of black hole mechanics in the bulk, usually with ABS thermodynamics. With ABS symmetry, the thermodynamics is a little bit tricky because you have these cosmic strings and you have conical defects, but we have removed all of them with our space-time surgery, so we don't need to be careful about that anymore. And you can actually explicitly check on the brane that this first law in the bulk induces these first laws on the brane, where the role of the entropy now is not played by the three-dimensional Bekenstein-Hawking entropy, is actually the generalized entropy, where for the gravitational system you have the walled entropy, which is the higher curvature theory generalization of the Bekenstein-Hawking entropy, and then you also have the entropy of the CFT. But you can compute things and you can see that this first law holds, and then you have the usual minus sign for the cosmological horizon. This corresponds to the fact that empty de Sitter is a maximum entropy state, but this is all usual in de Sitter physics fundamentally. And then now you can just go on and compute entropy, you can compute incapacities, you can do everything you want, rotation rate and so on. I'm going to just showcase very quickly one thing that I think is very interesting about de Sitter black holes, and probably is not very well known, and is its heat capacity as a Schottky anomaly. So what is a Schottky anomaly? This is common in just usual thermodynamics. If I take the heat capacity, which is just the partial derivative of the internal energy with respect to the temperature of the system, then if I consider a system with a maximum energy level state, then, for example, for a two-level system with energy gap delta, the heat capacity has a peak, and then actually instead of growing with temperature, it starts coming down again after starting from 0 temperature. And because black holes in de Sitter have a maximum mass, a bound on the mass given by this Nariai black hole, it was conjectured that black holes in de Sitter would have this kind of feature in the heat capacity. And for classical systems, it was checked in this paper numerically. And we kind of expand analytically on it, but we also find them for quantum black holes. So this is the heat capacity of our quantum black hole solution, and it does have this Schottky peak, and as we vary the back reaction, the position of the peak changes, where this ZS is basically the size of the horizon for the black hole for which the Schottky peak happens. The red line is just an analytic approximation, blue is numerically actually finding where the black hole, where this Schottky peak is. And that's pretty much it. I had some backup slides to talk about more Schottky peak, but I don't have time, so just going to the summary and outlook, these are the main points. Maybe interesting questions that we would like to explore eventually is, so these Schottky peak, are they actually trying to tell us something about the spectrum of the microscopic description of de Sitter black holes? Like, is there actually maximum energy state? Actually, if you consider charged black hole, the thing becomes much more interesting, because the Schottky peak sometimes disappears and there is actually a rise in the heat capacity as you then increase temperature again. So maybe more than a maximum energy state is a energy gap between the states that can close up as you increase the charge. So I think there is something maybe to say here. And then there are some other things like Festina lente bound or weak gravity conjecture that can be studied in this kind of quantum corrected black hole and see whether they survive in the quantum corrected geometry. And I think that might be an interesting playground to kind of test this kind of stuff. So yeah, that's it. Thank you.
Questions? So in flat space 3D gravity, there are also no black holes classically, but then there is a construction that one can understand just in 3D language, where you take a kind of a conical deficit that's very, very small.
Yeah.
So it's almost a cylinder. And then if you add some just perturbative matter, just some Casimir, some fields will have at one loop some Casimir energy on that circle, and then it can stabilize it and kind of turn the cone into a cigar in a sense, and then have a quantum correction black holes in flat space. Is your construction related to this?
Yes, so I think you're describing exactly these perturbative calculations that you can do, and up to linear order they give you a term that goes like the Planck length over R in the blackening factor, and that sources, you actually get a singularity at R equals 0, and then you also get a horizon. But those are all perturbative calculations.
But I thought that those in flat space, I thought those are reliable, because if you, I mean, the small parameter is that you take original conical deficit very, very small. Yeah. So then kind of that's your small parameter, and then that's you balance classical with one loop, but I thought that that's reliable calculation.
Right. I think
that two loop is suppressed. So you can.
So it is to some degree reliable, but at the same time, when you do this kind of perturbative back reaction with, for example, a conformally coupled scalar, the size of the horizon that you get is Planckian sized. So you expect quantum gravity effects to become important anyways at those scales, but
I thought, maybe I'm not remembering. Do you know the paper I'm referring to?
I think I know the paper.
Like Arkani Hamed and others. So you say that their horizon was Planckian? I thought that there was some parameter, but I'm not remembering.
If we are referring to the same paper, I think so.
So your construction also gives, in principle, flat space black holes that are kind of non-perturbative.
You can get them. Yeah, you can. There's actually, so the first series of paper in this topic was by Empran and collaborators. They looked at the ADS case and they described how you can get the flat space limit from there. It's a bit finicky. There is a review that we put out recently where we do that more carefully, but you can actually, you can actually get the flat space solutions anyways. Yeah. Mm-hmm. And it all depends on how you're slicing this ADS metric. So you can get both ADS, the sitter, or flat space on the grain.
I can just speak.
No, that's because you will not appear on recording then.
Oh, I see. Hi. Can you remind me what's the sign of the specific heat of this quantum black hole?
Sorry, the sign.
The sign of the specific heat, yes.
The sign.
Is it positive or negative?
So this is negative. You're talking about the sign of the specific.
Yes.
Yeah. This is still negative.
Okay, just like in higher dimensional.
Unstable. Yeah.
I see. Okay.
But if you include also charge, that what you get is you have the negative branch, but you also have the branch of that's with black hole close to the extremal solution, and that's actually positive. But that doesn't have a Schottky peak. So this Schottky anomaly only appears in the negative branch of the black holes.
I see. Okay. Yeah. Thank you.
Yeah. Yeah, so I guess this is what I'm talking about. You can get positive capacity if you include charge.
There are quick questions? If not, then let's thank Manuel again.